Okay guys, so this is class number 17 and I'm teaching you the continuation of the animation by the Matlab and using ODE solver to solve the differential equation in Matlab and hopefully the modeling. Okay, so it was noise. I want to reduce the noise. So before going to the notes, I want to just continue a fun simulation with you. You know how to make animation scientifically in the Matlab, okay? So I taught you how to simulate the squares and the circle, triangle, too many things, right? Now what I'm going to do here is that I'm going to say hey, r is equal to, I want to plot several circles together that they are moving, okay? Is say, I don't know, 0.2 centimeter, okay, meter, I'm sorry. Then I'm going to say 4 is theta between, oh, sorry guys, and the theta is between this and 2 multiplied by pi, that's right. And now 4, I'm going to move them. X, hold on guys, we have some fun guys with the loud music, hold on. Okay, we have COVID and too many people they got COVID in their brains. So now I'm gonna say for x of the center of this is moving from 0 to 0 to 0.1 to 10, and then I'm gonna say y of c is sine of x of c. Okay, sorry guys, this is the center of the circle I'm plotting right now, understand? So now if I say fill, as I taught you, fill what? So, and we know that the x of the first circle, x1, gonna be r multiplied by cosine of theta, that's right, as I taught you in the previous class, the first circle I'm writing here. This is, as a comment, please do it in the MATLAB. This is for plotting first moving circle, okay? And y of this, as I taught you in the part 15 or part 16, please go and check, y1 is sine, right? So, but when I say fill, okay, fill what? Fill x1 plus x of c, because I'm moving the center of the circle, that's right, and right, and y1 plus y of y plus y of c, and I'm going to say r. Let's see what we get here, guys. Hold on, guys. Okay, so and now we have this, okay? So if I run this, guys, what I'm gonna see, I'm gonna say and put the axis because I want to see what's happening, that's right, axis of between 0 and 30 and 0 and 30, huh? That's right. Now if I do that and then I save it as new anim, okay, in the ME202 class, and now if I do that, what I'm going to see is this. What is this? Interactive charts. No. Okay, what happened? x1 plus xc, y1 plus yc, but x is changing with this. Let me see if I don't know why it doesn't show me. Oh, I understand. Okay, where's the box? Hold on. Okay, Okay, today here is too many bugs, too many noise, and it's disrupting me. So I forgot to say figure 1. Okay, so if I do that, and I'm gonna do it like this, that's enough. So if I do that, you're gonna see that this is changing and bouncing this, right? So it's y is changing, right? So but this is too much, so I have to reduce this to, I don't know, and 3 to -3. I want to just make sure that this, see here guys, oh yeah, that's right. Here we go, you see the circle that is moving as a wave. Right, now you can have, say, hold on, you're gonna have fill this like this, and I'm gonna generate a second circle. I have a good news for you guys. So let me copy paste all of them. Please do that at home, okay? x2, x2, and you can have sorry, not this, and you can have, okay, yeah, so xc of 2, I mean xc of 2 gonna be, okay, cosine of, see this, we are moving the center of this, right? Cosine of x underline c, and this is gonna be sine of x underline c, huh? X underline c square. Who cares? So what I'm gonna do? I'm gonna change only the center of the circle. That's right. Right. So we double check. Yes. Yeah. That's right. So if I and I'm gonna change to the blue. So they have to be different, guys. Oh, what happened? Oh, there's a typo here. xc2, not x2, xc2 and yc2. See, these kind of the typos make your code funny. So see guys, here what is happening is a stick diagram. Because why? This is a take home message, because I have a hold on command here. Until you do not deactivate that, you're gonna see this kind of stick diagram. So I'm gonna cancel the code, okay? And now what's the cure of that? Intentionally, you're gonna say what? Hold off. I'm still in the for loop, that's right. I'm still in the for loop, and this is for, let me change it, seconds. Please do it at home with me, please, okay? Second moment. Now look at here what we get. I don't know, it's gonna be -5, and now let's run it. See, oh, huh? This is like the basketball play that is bouncing, and this is moving like that. Now we can generate a third circle. How? Just change the center of the circle, that's right. 3, 3, okay, and it's gonna be it's a random number, cosine of a random number, and it's gonna be sine of a random number, plus I don't know, a constant number 2. I can, that's right. So what you're gonna do, you're gonna say third one. So I intentionally do this because I want to teach you one thing. So 3, 3, and this is gonna be green. Again, guys, look at here. Fill, hold on. Fill, hold on. Fill, last fill you have to make hold off. If you have n hold on, if you want to make animation, you have to say hold off, because if you don't do that, as you saw, you're gonna have what? We're gonna have a stick diagram. Here we go. See? Obviously, you have seen that if you are around the 40 years old, in the previous Windows version 20 years ago, the screensaver was a black background and circles like that. That's right. Now you generated the screensaver of the Windows, almost one of the screensavers. Add more, huh? Add more. 4, 4. Now I'm gonna say, see, x of c, okay, x of c, and this. So here we go. So it's just funny, right? But this is the powerfulness of the coding, okay, in MATLAB. Now you know how to make the things. Now after having this, now let's go to our what's clear. Let me go to our nodes, because the last topic of this course is the ODE. So where is that? MATLAB, okay, and the notes, right? It's recording. Yes. Okay, guys, you're on the last note, huh? So solving ordinary differential equations. You will eventually see ordinary differential equations in many courses like dynamics, vibration, robotics, undergraduate and graduate control, system dynamics, fluid mechanics, and even heat transfer. So it is now a proper time to briefly learn it and then solve through MATLAB. As you know, we show displacement as x, its time derivative velocity as x dot in mathematics, that's right, and its second time derivative acceleration as x double dot. I'm pretty sure that you have aware of your car velocity and acceleration every day. Just push your gas pedal. Now if you add the displacement, velocity, and acceleration like this, mathematically add them. Acceleration plus velocity plus displacement is equal to 0. You just generated a simple, namely ordinary differential equation. In abbreviation we say ODE. ODE. This is the simplest version of a linear differential equation. Yes, you did it. How to solve it analytically? Forget it for now, because you need to go to algebra class. You learned or will eventually learn. What we do care is how to solve it numerically, not analytically, okay, through MATLAB. Okay, let's do it. But before that, we need to know some basic definitions. The first one is state variable, as I did, if you remember, in the first classes. In all fields of engineering, we define state variables as follows. Equation 23 and 24. I'm just reminding you. Z1 is the position or temperature or pressure or length or whatever. Z2, second state variable, is time derivative of that Z1, position or temperature or pressure or length. This is a standard definition of state variables in engineering. So if you have Z1 as sandwich, Z2 gonna be sandwich dot, time derivative of sandwich. If you have Z1 is pizza, Z2 gonna be pizza dot, time derivative of pizza. Simple as like that, okay? For an example, we define state variables with respect to displacement x and velocity x of a moving object, like your car or hand, because when you're moving your hand, it has some displacement and has some velocity. The same for the cars, right? So Z1 gonna be position of your car or hand, Z2 gonna be first time derivative of that. Or for pressure of a fluid tank, you will see in ME330 course, they become as the pressure of tank gonna be Z1, Z2 gonna be the time derivative of the pressure of tank that is changing with time probably. Or for temperature of your living room right now, if you have temperature as the Z1, state variable Z1, Z2 gonna be time derivative of that. The change of temperature in the living room when you open the window or open the door. So taking time derivatives of equations 25 and 26. I mean this 25 and 26. I'm taking from the both side time derivative. So it's gonna be z dot 1, look at here, z dot 1 is equal to x dot. That's right. So z dot 1 is equal to x dot, but we know that the x dot we defined as what? As z2. So z dot 1 is equal to x dot is equal to z2. Now the other equation, time derivative of this, z dot 2 is x double dot. That's right. Z dot 2 is x double dot. But we know x double dot from this equation. As example, x dot double dot is minus x dot minus x. These terms goes to the other side. That's right. Look at the finding an unknown variable. Here we go. That's right. So but we know that what? We know that x dot is how much? Z2. X is how much? Z1. I'm just replacing there, guys. So minus z1 minus z2. Understand? Now I'm removing these. So now equation 31 and 32 are called state space equations. This is definition in control, guys. Specifically in ME 696, when I'm teaching the next semester for grad students, they're gonna see this. This is state space equation. Yes, you simply like that. You will see it soon in other courses. MATLAB exactly uses this formulation, state space equation, to solve an ordinary differential equation. So we need to define state space equation through the following code. Now let's go to MATLAB. So now that we change our this simple differential equation, this, okay, to state space. Now exactly we are typing this in MATLAB, these equations. How? I'm going to teach you. So I'm closing this, opening this, and then I'm writing function, as you see, exactly this function. So what are our state variables? Z1 and Z2, and we are taking time derivative. Derivative means d, so dz, because your z means the derivative of state variables is equal to. Now you can name this function as whatever you want. Sample, I say sample. You can name, I don't know, whatever, Jackson, whatever, okay? So t, what are the variables in the differential equation? Time derivative. So we have t and z state variables. Always you have to do that, okay? So then you can put, as I said here, comment, we here define space for state variables and clearly time, because in differential equation you are dealing with the time, which is an inevitable part of an ordinary differential equation. This is common. This is good. Common thing is good. So now, because here I had two state variables, going to be dz is equal to, I am generating a space for them, zeros. Remember the zeros comment I taught you? Go to the YouTube links. You have two state variables, 2 and 1. It generates is this. Look at here, guys, for refreshing your mind. Zeros, 2 and 1. 0, 0. That's right, generating a space. I'm just explaining this. We have two state variables, we have 4 state variables. So if you have 4 state variables, you need to use dz is equal to 4, 0. A vector of 4 zeros. That's right. If you have 10 state variables, you have to say zeros 10 and 1. If you have 20 state variables, say zeros 10 and 20 and 1. So now I'm exactly this, you see here? This, I'm typing in the MATLAB. How? I say dz1 means derivative of z1, z dot 1, exactly this. This is how MATLAB understand. Is equal to z2. See, underline in the ODE is like this. Now dz2 is equal to what? Minus z1 minus z2. Bingo. Now you transferred your differential equation to state space, and now you are coding in MATLAB. Here we go. Now, after doing this, I'm saving this Control and S. And the name of this must be exactly, guys, the name of this what you define here. If you say sample here and you put the payment, it's gonna fail. The name of this, I'm repeating, must be exactly like name of this. So sample, define a sample. Now we define the equation. We need the solver for that. Okay, another file. Now save the above code as sample.m MATLAB file. Note that the name of m file and function must be the same, as I said. Now use the following code. I'm just typing. I will upload the notes on the blackboard. So clear, as I told you several times, and the clear all. It's gonna be helpful for you. Clear all. Okay. Now you have to do this. Capital T means for time vector. Capital Y means the Z1 and Z2s. It can return you a matrix. Okay. So, and you can say capital Z because you have two state variables. Now we have different solvers in MATLAB, guys. ODE 15, ODE 15S, ODE 45, ODE 113, ODE, if I'm not wrong, 113S, ODE, too many solvers. What's the difference between them? This is not in your level, okay? But the best solvers for your level is ODE 45 and ODE 15S. Just accept from me, ODE 45. Exactly, you do this. Bracket. Now, as I told you, MATLAB @ means go and call. Call what? This function. Which function? Sample. When you write this, when you run this code, it goes and calls whatever is inside this function. That's right. Now, you have to define what? The time interval you want to simulate the ODE, solve the ODE. And I want to solve it for 2 seconds. Starting from 0, step is 0.05 and 2 seconds. But you have to have some initial conditions for the Z1, which is displacement, for Z2, which is velocity. Suppose this is the displacement and velocity of your hand. So I'm saying that its position is located at 0.3 radian and its velocity is 0.4 radian per second. Or if it is for car, the same. And now we did it. Understand? Okay. So, and now I'm running this, guys. First, I'm gonna solve it. Save it as solver of sample, whatever you name. Here you go. This is arbitrary. You can select any name. Okay. So now I'm solving that, guys. When I solve that, you see that it gives you t, a vector of t's for 2 seconds, and solves your z and z1s and z2, means position and velocity of your car or your hand. But this is ridiculous. You have to plot that. That's right. But I taught you the tool how to deal with them, because your z is what? Is a vector of 2 columns and lots of the rows. So you're gonna say figure 1. Now I taught you. So figure 1. Plot. I'm just typing from here. Plot the all time t, capital T, and all, because I changed to z. Look at here. I'm gonna plot all this column of z. So it means all the rows, as I taught you in the matrix operation, all the rows and first column. That's right, I taught you in the YouTube link. All the rows and the first column. That's right. And plot for me in the blue. Okay. Then this is common. This plots position versus time. Because this is for Z1. That's right. Position. That's right. Then I'm gonna say grid. Okay. Then X label. Okay, time in second. Okay, and the font size font size, as I talked to these commands previously, I'm saying 10. You can change it to what? To a LaTeX interpreter to make it more pretty, that's right. So this is gonna be displacement X in meter, that's right, Y level. So now if I run this, guys, here we go. This is displacement of your car, and initial condition was here what? Let me show you. 0.3. Starting from 0.3. At time 0 is initial condition. Is 0.3. So this is, you can plot the position or of your car or your hand through the differential equation, but numerically for 2 seconds. Understand? Huh? Now I can do the same and go to figure 2. Oops. What I have done. So figure 2. I'm saving time, that's right. Only the Z2 or the velocity of your car, it was in the second column, that's right. Bingo, exactly like this. But I'm gonna say plot it for this, and then I'm saying here the Y level is the velocity dx. That's right. And here we go. See? This is dx, velocity. Its initial condition was what? 0.4. Here we go. It shows the velocity of your car or hand with respect to time. I'm going to change like this. Obviously, if you change interpreter to LaTeX, okay, LaTeX, obviously you're going to have more fancy what interpreter get here. See, it's more fancy than this font. So I'm gonna change it to 50 and I'm gonna copy and paste everywhere. There we go. Please do it. It's a good practice for you. Right? Now look at here what we get. See how it looks like. Now you can say, because you're in the LaTeX, you don't need to type like this. In LaTeX you can say, as I talked to you several times, you can say, okay, in LaTeX you can say is dot x. This is how we write in LaTeX. So if I do that, see the difference, guys. X dot. Sorry, not dx. Understand what I'm talking about? So we did it. So we solved the differential equation and we solved the equation. Note that at called sample m file stress equations, this is the time interval. You can change it like this, guys. You can change it to, I want to see 5, and I'm gonna start from minus 0.3 to 1, whatever. Okay, see the difference? So this is for 5 seconds, and starting, this is from 1, I said, for the velocity, and this is pointing from minus 0.3, and this is what we have. Understand? So if you increase that to, I don't know, 25, as you will learn why in the control classes, they eventually goes to 0. This is not the place that I teach you why. Okay, see, both they go to 0. Because the system has damper and has a stiffness, forget about those. Why they both go to 0. So we do need initial conditions for solving ODs, as I taught you. For example, assume equation 22 is OD of your car suspension system. Equation 22 is like this, that's right, as we did, that's right. And I explained everything by hand, okay? Now, guys, as practice, please solve the following ODs with these initial conditions. Solve these ODs with these initial conditions, guys. Okay. For example, I'm doing this one, number 1. Okay, so if I do that, where's the pen? If I do that, its state variable is gonna be like this: z.1, please do that home to double check. z.2 gonna be how much? Minus 4 z2 minus 10 z1 plus sine 40. In the vibration and control, you see that this is the external force that we are applying to the system. This is harmonic force that we are applying. I'm going to teach that. Okay, so what I'm going to do, I'm going to only change this is the same. Here you have, let me go down. Oh, I'm in this. So here you have minus 4 multiplied, don't forget multiplied, star, minus, oh, this is z2, 10, that's right, multiplied by z1, plus sine 4t multiplied, that's right. So initial condition is 0 and 0, guys. Initial condition is 0 and 0. I want to just run it for 5 seconds. Let me see what I get. Oops. As expected, the both velocity and the position gonna oscillate because you are forcing your system to oscillate. In differential equation, right hand side is for the external force. The left hand side is the natural response of the system. So you, by looking at this, you're gonna say, oh, I want the system by my hand be subject to a harmonic force. Here, there's no harmonic force. Let me show you. Here you have this harmonic force. Here you have sine and cosine 2t harmonic force. Here you have incremental harmonic force because you are multiplying a linear t by sine of t. That's right. So you saw that. But we have another kind of the plotting, guys, in MATLAB. Figure 3. I'm teaching you because you can say plot. Instead of plotting your position, velocity versus time, you plot them versus each other. The name of this plotting is phase plane. In nonlinear dynamics and control, it's very, and stability analysis of the system is very interesting things. Okay, so, and the grid. And now your x and y are gonna be different because your x is x, that's right, and in meter, and your y is no, y3. I'm sorry, 2. Okay. Okay, guys, look at here. What you get? The name of this is phase portrait. Okay, or phase plane. So you are plotting velocity versus displacement, and you see it's giving more sense of interpretation. It says that your system starting from 0 and 0 and finally gonna follow a harmonic force that you apply to the system. Understand? That you apply to the system. Huh? So this is, and two many things. This is the stable periodic motion, and you're gonna learn eventually if you go to grad school. You're gonna say limit cycle, chaotic dynamics, too many things. Okay, this is another type of plotting in MATLAB. Now you can use, guys, these vectors, each of these, to make a simulation. Oh yes, you can. Okay, yes, you can. How? Suppose that I wanna say what you're gonna do first. There's a noise, guys. Hold on. Okay, so actually, you know what, guys? I want to leave it as a challenge to you. I don't want to teach you now. So I want that you combine the animation skills that you learn, combined with these, and in the final, I want to challenge you. That's a good idea. Okay. So, and we are done.